So now let's talk about some new reactions, okay, things that we didn't cover before in Chem 261. The main one is oxidation and reduction. So I'm going to draw for you a very common series that is used in chemistry and biochemistry, which is you can take an alcohol and you can oxidize it by adding CO bonds. So if I just get rid of this H and I make a C double bond O instead of a single bond O, then I've got this series, and it continues on to adding even more O. If I could use this weak bond here, CH bond is susceptible to oxidation, which means an oxygen can insert itself in that bond. So let's highlight what's going on here. This is an oxidation series. I'm looking at one CO bond, now two CO bonds, now three CO bonds. I've increased the number of CO bonds, and that is one way of thinking about oxidation in a really simple sense. Another way is by looking at the reverse. If I take away CO bonds, I'm doing what we call reduction. You can also think of reduction in terms of adding hydrogen, CH bonds. So going from here to here, I've added an H, CH bond. So that's also reduction. Let me show you that real quick. Going from here to here, I've added an H here. So that's called reduction. So reduction has this symbol, oxidation has this symbol. That's an O. Okay? So let's take a look at this reaction here. I have CO single bonds, and now I'm getting rid of them. All right, so let's take a look at these examples, and of course the first one's actually a little bit difficult, so let's skip it for now. We'll come back to it. For B, it's quite simple. I think you see CO bonds here, and here are three CO bonds. So we've increased our CO bond. We've also decreased the number of CH bonds. So for both reasons, this is oxidation. For this one, I think you see the removal of some C double bond, CO bonds, or a C double bond O. So we are decreasing our oxidation, so we're increasing reduction. And you can also tell based on the addition of hydrogens right here. So to take the place of oxygen, we put down hydrogen. Increasing CH bonds is also called reduction. But with this one, we're changing something. It's different. It's got Cl instead of O. So that doesn't necessarily mean it's oxidation or reduction, because Cl is sort of equivalent to O in a sense. So instead of one O, I'm maintaining a certain level of oxidation by having Cl. And here, I haven't added any CH bonds to this carbon, whereas you saw that here I got rid of a CH bond, and here I added CH bonds. So usually that's a clear indicator. So here, since I'm not doing either, this will be neither oxidation nor reduction. Now Klein has a way of going through and using some oxidation numbers for you, but I like to just most of the things you can tell are oxidation or reduction just by looking at the oxygens and hydrogens. So only sometimes will you get neither, meaning you haven't added or changed the number of hydrogens to a certain carbon. But I highly recommend this little square over here. You guys learn your oxidation series going from alcohol to aldehyde to carboxylic acid, and then learn your reduction series is the reverse, carboxylic acid to aldehyde to primary alcohol. Okay, can also have a secondary alcohol, but it has oxidation only to a ketone. It doesn't have the ability to break the CC bonds, only the CH bond to put an oxygen in there. So just be aware. So oxidation is secondary alcohol to a ketone, reduction is ketone to a secondary alcohol. And then if you have a tertiary alcohol, I think you guys see there's no hydrogen to insert an oxygen into. So here we have a hydrogen, that's why we could make a double bond. Here there's no hydrogen, so this does not get oxidized. So there's no reaction for tertiary alcohol. It's already saturated, there's no place to insert oxygen here. So when you go to an alcohol, notice that this reaction goes to an alcohol. We started with something more oxidized. So you can reduce things that are more oxidized. And what are those things that are more oxidized? Well, they're aldehydes, carboxylic acids, or ketones. So those are the kinds of functional groups you expect to see. All right, so I put aldehyde specifically because it's in this example, but in parentheses I put ketone because that's also possible, and then also carboxylic acids. Now, 3 reagents we can use to do reduction. There's different kinds of reduction. So there's a reduction of the carbonyl group. And so what's going on here is we're changing the carbonyl group using sodium borohydride in methanol or lithium aluminum hydride followed by water workup. Often I don't see these mixed together. I just want to make note that sometimes this one is also shown as 2 steps, and the second step could just simply be water. So just these 2 reagents are very similar, either NaBH4 or LiAlH4. By the way, lithium aluminum hydride is often abbreviated LAH, La. Okay, La, La, La. All right, so if you see that, that's just a reducing agent. Now notice there's another kind of reduction, which is of the pi bond as well, and the carbonyl group. And so a really good reducing agent for that is just like we've learned before with pi bonds, H2 on palladium, platinum, or nickel is fine. But make note that H2 will also reduce the carbonyl group. So keep that in mind. All right, so based on this chart, if you have an alkene, be careful, you're not just reducing the carbonyl, you're also reducing the alkene if you use H2, catalytic hydrogenation, so some kind of catalytic metal there. If you wish to keep the alkene, you should use something that's less reductive, so something that will only reduce the carbonyl group, so sodium borohydride or lithium aluminum hydride. Now what these reagents look like, it's good to draw it out. You have a sodium salt and it's BH4. So this is very similar to, I know you've seen boron in the hydroboration reaction, a BH3. A BH4 means it's got an extra hydrogen on it, so you got the boron in the center, and it bears a negative charge when there are 4 groups around it because its valence is only 3 electrons, so when it has access to 4 then it feels more negative charge. This is a positive over here. Okay, so LiAlH4 is similarly aluminum in the center, and aluminum is also in group 3, so when it has 4 hydrogens it's negatively charged. Lithium is positively charged, counter ion. Okay, of course you know by now these counter ions we don't really care about, they float around in solution. It's really these groups that are important, and of those it's the hydrogens that are important. So what's really reactive are these hydrogens. Okay, so there's 4 of them, but we only really need 1 of them to do the reduction here. So what we're going to do is show that in the next step we see NaBH4 reducing agent, and just think of it as a source of hydride. So when that hydride comes off you get BH3, which is more stable. So for our purposes, whenever I see LAH or NaBH4, I'm going to think hydride. I'm going to think hydride ion. Okay, so technically it's not just floating around by itself, it's on the borohydride, but I think of it as a shortcut. So when I think of this, I think of it like a nickname or shortcut is hydride ion. And the way that behaves is it's a nucleophile. It's negatively charged, strong base, good nucleophile comes in. And it's not super good nucleophile compared to bromide because it's not so polarizable, but considering what else is in solution, it's the best one we got. So when you do that, we're going to end up with negatively charged ion here, our hydrogen added here. And then to get it neutral, then we have protonation by methanol. You can just grab this H, and then you can get methoxide as a side product. Now notice the stereochemistry is to get the enantiomers because this is chiral here. So where does that come from? Well, if you look at the attack in the first step, this hydride is attacking a planar carbonyl group. Carbonyl groups are flat. So the hydride can come in from the top or it can come in from the bottom. So that's where you get these two different stereoisomers. Now, Klein seems to just interchangeably use NaBH4 versus lithium aluminum hydride, but to me, lithium aluminum hydride is a lot stronger reagent. So I tend to only use LaH when I have to. If I see an aldehyde or ketone, they don't really need LaH. You can do those reactions with sodium borohydride. When I would use LaH is if I have something more oxidized to reduce. So if I have something more oxidized, I got to hit it stronger to reduce it. So I would generally reserve LaH, and I recommend you do the same for esters, so meaning it has another oxygen in it, or carboxylic acids. That's when LaH is really handy, is when you have more oxidized substrates to reduce. Okay, otherwise NaBH4 is fine here for just little aldehydes and ketones. Okay, but in any case, let's reduce these. We have a reducing agent here. What would you get as a product? And remember, we're going to reduction. This is oxidation. We're doing the opposite. We're doing reduction. So what would be the functional group we get? Well, this is our oxidized part of this molecule, so we need to reduce it. So that means I need to add a CH bond to it. So to add a CH, I'm going to have two H's now, and I'm going to have a single bond to O, and then I'm just going to make that neutral, so I'm going to do that. So this is the alcohol. So aldehyde comes from a primary alcohol, and the generic symbol for alcohol is ROH. All right, let's try this one. What do you guys think is the molecule that we get after reduction? Okay, so similarly, I'm going to attack this hydride right here, and then that will show how I end up with a single bond. And then I'm going to protonate that with the water work up here. This is negative, and it grabs a hydrogen here, and that's how I get that to be neutralized. Just one note here, often you see the phenyl groups as abbreviated pH. So I just want to bring that to your attention, that you might see that on standardized exams. Don't freak out. It's just just an abbreviation. Trying to be helpful. Okay, so sometimes you see that. All right, along the same lines, we can apply this to multiple carbonyls to get multiple OH groups. So for diols, you just need 2 carbonyls and reduce that. Again, which one of these reagents do you need to be careful of if you have a double bond here? I think you remember H2PD, it can reduce double bonds. So if I had a double bond here, then this first reagent is going to reduce it, so I'd have no double bond here. But if I use these guys here, then they will not be able to reduce that double bond, so I'll still see the double bond in that case. And then the last thing about oxidation here is when you want to oxidize an alkene, then you can use 2 different routes here. One is you can use MCPBA or some kind of peroxy acid, and the peroxy acid will insert itself into the pi bond and make an epoxide. So the intermediate is going to look like this after MCPBA is used. And then this is going to open up with water. Water is going to attack and open this up. And that's how we get a trans diol. So this is a trans 1,2 diol. If you don't want the trans and you want cis, then you want some kind of reagent that delivers the OHs on the same side. So in a different color, I'll show you. OSO4 sort of is osmium tetraoxide. And these oxygens go onto the same side, delivered by OSO4. Okay, so then that's why they're syn. Another reagent you can use instead of OSO4 is cold KMNO4. If you control it, if you don't heat it too much, it won't cleave the double bond, because hot KMNO4 will cleave the double bond and open up the ring. If you use cold controlled KMNO4, you can get the O's of KMNO4 to do the same thing here. Okay, so this will give you your syn or cis 1,2 diol. So if you ever see 1,2 diols, now you know how do we make those. They can come from an alkene.